Hello, and thanks for stopping by. My name is Amy Christensen, and I'm going to walk you through my poster, which is entitled Differences in Fine Particle Chemical Composition on Clear and Cloudy Days. In the poster booth, I've uploaded a PDF version of this poster. Feel free to download it and peruse it. I will also give a virtual walkthrough of the poster here. Additionally, the paper on which this poster is based was recently accepted for publication in Atmospheric Chemistry and Physics and can be read there. A link to the discussion paper is also included in the poster booth. First, let's go over a bit of background information. At any given time, visible clouds cover over 60% of the Earth's surface. Clouds alter fine particulate matter, or PM2.5, mass and chemical composition, generating particle mass aloft, such as sulfate and water-soluble organic carbon. This cloud processing alters physical and chemical parameters of aerosol, including size distribution, hygroscopicity, and O/C ratio. Currently, aerosol-cloud interactions and their impacts are a critical uncertainty in model projections of future climate. Traditionally, PM2.5 is characterized via surface measurements at ground monitoring stations that measure, for example, every 3 or 6 days. Satellite measurements of aerosol optical thickness, or AOT, can be used to improve upon spatial and temporal limitations in PM2.5 assessments, as they view the entire Earth's surface every 1 to 2 days. However, satellite retrievals that are impacted by clouds are often removed from final data products due to increased error that occurs during cloudy times. This leads to an implicit clear sky bias in our understanding of PM2.5, as concentrations from satellite measurements only occur during clear sky periods. This bias may hinder quantitative assessment of tropospheric chemical composition during cloudy times, which is essential to accurately understanding aerosol cloud interactions. In this presentation, we investigate quantitative differences between PM2.5 mass and chemical composition during cloudy and clear sky times, with a focus on the ways in which hygroscopicity and aerosol liquid water, or ALW, change under these conditions. To assess these differences, we use a combination of surface PM2.5 chemical composition, meteorological information, thermodynamic modeling, and satellite information. First, we take chemical composition information from the improved network and combine it with meteorological information from the NAR, which is necessary to perform ALW mass concentration calculations in the thermodynamic model Isoropia. We pair each improved surface measurement with MODIS overpasses and use the MODIS cloud flag to determine if the surface measurements were done under cloudy or clear sky conditions. If MODIS was able to successfully retrieve AOT, then the improved measurement is classified as clear sky. If MODIS did not successfully retrieve AOT, then the improved measurement is classified as cloudy. As a point of clarification, AOT measurements from MODIS were not used in this assessment, only the cloud flags. After classifying each measurement between 2010 and 2014, we separated the measurements into 3 scenarios for ALW calculations: clear sky, mixed, and cloudy. Figure 1 explains these scenarios in a flowchart. In the clear sky scenario for ALW concentrations, we combined clear sky improved chemical composition measurements with the corresponding clear sky meteorological information from the NAR model. Similarly, the cloudy scenario combines cloudy improved measurements with cloudy meteorology. The mixed scenario combines clear sky chemical composition with cloudy meteorology. And it is a thought experiment that's meant to imitate studies in which cloud-free growth factors are eventually applied to models and used to simulate cloudy meteorological conditions. This also allows us to separately investigate the impacts of meteorology and chemical composition on hygroscopicity and ALW. I then compare all scenarios to each other and test for significant differences. Figure 2 shows all the locations and regions in which we tested these scenarios. In this poster, we focus on the eastern United States. Further, we examine the Mid-South region as a case study, which is circled in red. Before I delve into the in-depth results of this research, I want to leave you with the main take-home messages of this study. Hopefully this is also helpful for those pressed for time, and that we will get the main message of this research without sitting through my entire talk. Here's the main message. ALW estimates in aerosol growth due to water are highest during cloudy times, the times when satellites cannot sense particle properties and impacts. This limits our understanding of atmospheric particle burden and its climate-relevant physical and chemical properties, which have implications for the prediction of weather, air quality, and climate. This clear sky bias affects our quantitative understanding of ALW on cloudy days, which hinders model representation of aerosol cloud interactions. Accurate representation of ALW, aerosol cloud interactions, and subsequent radiative forcing estimates require chemical composition information during cloudy times. Now I'll move on to discussing my results in more detail for those who are interested. In these results, I focus on the eastern United States because the ALW concentrations are largest in this region, and it is in cloud often and consistently, making statistical comparisons more robust than the western US, where cloudy counts are low in most seasons. The first figure shows seasonal cloudy and clear sky median chemical constituent concentrations in the eastern US. Each group of box plots represents a different region. Within a group, seasonal medians are shown, starting with winter on the left, then spring, summer, and finally fall on the right. The bar on the left in each group pair is the clear sky concentration, while the bar on the right is the cloudy concentration. Red represents sulfate concentrations, blue nitrate, and green total organic carbon. There are significant differences in chemical constituent concentrations between cloudy and clear sky times for each chemical constituent, and these patterns are explained by differences in emissions and in situ chemistry during cloudy and clear sky times. This also impacts particle hygroscopicity and ALW, as is shown in the next figure. This next figure illustrates the same regions, but this time has box plots that show the distribution of ALW concentrations during clear sky and cloudy times in each season. The yellow box plots are clear sky conditions, and the blue box plots are cloudy. Again, seasons are shown from winter on the left to fall on the right. In most seasons and regions, cloudy ALW concentrations are higher than clear sky, with few exceptions. This pattern arises from a combination of higher relative humidity during cloudy times and changing aerosol composition that affects hygroscopicity, which I'll explore more in the next figure. In this third figure, we investigate the impacts of RH and chemical composition using the three scenarios I mentioned earlier: clear sky, cloudy, and mixed. The table here represents what parameters are used for each scenario. In this figure, I want you to focus on the last panel, panel F. Here I show the distribution of ALW concentrations for each scenario. Yellow is clear sky, cloudy is blue, and green is mixed. The only difference between the mixed and cloudy ALW calculations is that the mixed scenario employs clear sky chemical composition extrapolated to cloudy meteorology. When we do this, we find that monthly median ALW concentrations in the eastern US are significantly different from cloudy in all seasons except winter. Cloudy times is our best estimate of what ALW is like under cloudy conditions, since that scenario uses the actual chemical composition during cloudy times. Generally, mixed ALW is higher than cloudy because clear sky chemical composition tends to facilitate higher hygroscopicity, and cloudy RH is elevated. This highlights the fact that a changing PM2.5 chemical composition has a determining effect on ALW mass concentrations, which are critical in the estimation of aerosol-cloud interactions and particle radiative impacts. The last point I want to talk about is the one involving the case study in the Mid-South, which is summarized in the table at the bottom. Here, we calculate growth factors for this region under clear sky and cloudy conditions using the equations shown. In each season, we highlight the values that are higher between clear sky and cloudy times for growth factors, ALW, RH, and nitrate. We find that growth factors and ALW are higher during cloudy times, and absolute values are highest when RH and nitrate mass fraction are highest, which occurs during winter and spring. This further illustrates that chemical composition is essential for understanding water uptake and aerosol cloud interactions. So to summarize, PM2.5 mass and chemical constituent concentrations differ significantly between cloudy and clear sky times. These patterns cannot be explained solely through physical meteorology, such as relative humidity. Rather, a knowledge of emissions and in situ chemistry is needed. Chemical composition also changes sufficiently between cloudy and clear sky times to affect hygroscopicity and alter predicted ALW beyond differences in meteorology alone. Finally, growth factors in the Mid-South are highest during cloudy times, especially in winter and spring, when nitrate mass fraction and RH are highest. From this research, it is clear that our representation of ALW during cloudy times is hindered by the clear sky bias. ALW estimates and aerosol growth due to water are highest during cloudy times, the times when satellites cannot sense particle properties and impacts. This limits our quantitative understanding of ALW, atmospheric particle burden, and the climate-relevant properties of aerosol. Accurate representation of ALW, aerosol cloud interactions, and subsequent radiative forcing estimates require accurate chemical composition information during cloudy times. Thank you for visiting my virtual poster. I'm happy to answer any questions you may have, either through the live chat function or via email communication at the email addresses listed under the title and authors on the poster.